Here's another really sneaky trick you can do with this transit data, what's called the Rossiter Mclauchlin effect. The idea is you can actually use the transit to find out about the rotation of the star that you're orbiting.
So here we have a star that's going and a transit's going to occur. And so this shows you where the object is as a function of how bright the star is as a function of time.
But of course the star is rotating. This part of the star is coming towards us, that part is going away from us. So let's colour it now. So the blue is the bit that's coming towards us because the spectrum from that is going to be blue shifted, and the red bit is red shifted. So as the planet goes across, it will block out some of the blue light and then block out some of the red light. So as it's blocking out the blue light, the star will appear to be moving away from us a bit anomalously. And when you block out some of the red light, the star will appear to be moving towards us. So the velocity of the star will appear to go away and then come towards us.
Right, and so you can actually go through and measure literally how the star's rotation compares to the motion of the planet.
Now what you'd expect is that the planet would be going around the star in the same sense the star is spinning around itself, like in this diagram here. In our own solar system this is the case. The direction the sun is spinning and the direction all the planets are going around are the same. You'd expect this to be the case because both the sun and the planets form from the same protoplanetary disk. So this is what you'd expect. Yep. But I suppose for completeness sake we should consider the alternative possibility, which is they're going in opposite direction. In this case, the star's spinning the same way, but now the planet's going to come in from Brian's side.
Right. And so it comes here, blocks the red side first, and so it's going to appear like it's moving a bit bluer towards you. It's going to be moving towards you when it comes on this side, relative to when it blocks out the blue light, which is the part which normally indicates motion towards you.
And this can be measured and has been measured multiple times, and here's one example of this. And the results were pretty surprising. It turns out that between 45 and 85% of hot Jupiters are misaligned, are more than 30 degrees out from the same plane as the stars going around.
So these are completely different than our own solar system, and it's really bizarre because clearly these objects are being formed from the same gas as the sun. I mean, they're not being drifted in from interplanetary space or something. So, and yet we're looking at this and it's like they almost don't even know about what what made the angular momentum that made the star in the first place.
So this is pretty baffling at the moment. We've got a couple of ideas about what might be going on here. One idea is that maybe you actually had two protoplanetary disks. Maybe you had one disk that formed the star, and then it went away, and then another disk got dumped down at some later stage with a different angle and formed the planets. I mean, why not? Another possibility is it's this whole billiard stuff, the planets scattering off each other. But if you ever play with a simulation, it's quite hard. You tend to even end up with things still going the same way around. But if you work on it a bit and maybe have enough time and allow them very slowly to work themselves up, maybe you can get them into these really weirdo orbits.
All right, so still another mystery on our hands.